Now let's talk about cases where you have a collection, but you don't want to have duplicates or elements of the same value equals. So if I have a vector, for example, vector of integers, I can have the same element multiple times with, and there's no problem with that. But let's say that now I want a data structure where if I put 2 times the same element, I either get an error or I get the second element not inserted. So it will ensure that my such data structure is called a set. So if I have a set of something, so there are several implementations of a set. So we have a hash set, and we have B-tree sets. Let's start with a hash set. So do a hash set like that. This is a class, or this is an object from the main library that you need to import. So I have to import by the IDE. And now the only zigzag I have here is because, like before, when I had empty vector, the compiler doesn't know what is the type of the elements of my set. This is actually, I can either precise that by putting a type annotation. I can do it and say that it's a hash set of I32. But I can also, the compiler is quite smart, and it can also infer that if I insert an element, for example, 5, by the fact that 5 is I32, now the compiler has enough information to deduce that the type of set is I32. So let's try this, and let's try to print the elements of my set. If I do this and I want to print the set, you can also see here that there's a problem, because it says now that for a set, there's no implementation by default of a way to print a set itself. So you can print elements of a set, but by default, there's no way to print the whole set. This is not a big issue, but because it has an implementation for debugging printing. So the only difference is that for debug printing, I should do colon question mark. So let's try this program. And you can see that it has printed 5, my element of the set. And if I insert another element, let's say I insert 1, now it would print 5, 1. And if I insert 1, 5, so 1 first and 5 later, you can see that it still prints 5, 1. And that's because for set, the order is not defined. So even though I insert it in this order, 1 and 5, the internal representation of a set does not preserve the order. And when I print it, it will enumerate the elements in order that is not deterministic. So let me remove the vector here. I don't need it anymore. Now the question is, what is equality for a set, for elements of a set? For our I32, it's very obvious that you expect the equality to mean that the values are equal. So if I insert 1, 5, and insert 1 again, I do a duplicate. I don't want to have 5, 1, 1. I just want to have 5, 1. And we're going to check that. As expected, I only have 5, 1. So I insert 3 values, but because 2 of the values are equal, I only have 2 elements at the end. But the question is now really that, okay, for this set, which is a set of integers, it's very obvious that the equality means that the value should be equal. But what if I do a set of something that I define myself? So let's define a struct, let's say a point that has two values, x and y. I define it like this. We saw that for a structure, we can have anonymous members. And instead of having a set of integers, I now have a set of points. So I would say point, let's say 0, 0. Now, if I do that, I have a lot of errors because now my stuff is not consistent. First, I have the fact that I inserting a point and then afterwards I insert numbers. So we saw that for a collection, all the elements have to be the same type, and this is not true here. I have a point and now I have integers. So these two guys are errors. Now the second error here is that when I try to print element of my set, I have an implementation, a debug implementation for printing, but I don't have that for the elements itself. I used to have that because elements were integers. Integers have debug print. But point by point is my own structure, and by default, Rust does not generate any code for you. So now I have an error for that. The second error we're going to fix right now using derived macros. Derived macros are pretty useful. There's a bunch of, you add them, they look like annotations, but they actually do much more than that. So they are basically code generators. If I put this keyword here and then followed by some implementation of some word, some keyword, I have the compiler will generate an implementation for that. So here I want debug print. So I want to go debug, and the compiler has now has used some external library. For the case of debug, it's actually part of the standard library to add code to my class so that it's debug printable. In this case, for this to work, all it needs is that each member of my struct is also debug printable, which is the case because it's I32. So that eliminates the second error, but you can see that I still have the first error. Okay? And if I hover over this error, I have a message that a little bit cryptic. The trait bound point std cmp equal is not satisfied. And same thing for the trait bound point std hash hash is not satisfied. So what it means is that my hash set requires the members, the type point, to have some trait, which is some interface, if you prefer, some shape. So we had the same issue here with I printed debug printed the set. Debug printing the set also required my point to have debug print. So I derived debug print. So likewise, I can also add implementation that is missing by saying that they want equal and they want hash. Let me then put equal and hash and see how it goes. So hash seems to be fine. There's no error, but equal has an error. So if you go here, it says that equal needs partial equal. So currently you can say, okay, what am I doing? It seems like I'm just fixing the stuff by using the compiler to guide me, which is a perfectly fine way to do things. But maybe we should have a better understanding of what's going on here. But now, for a moment, just fix the errors, and now we have no errors. We can run this. And you can see that it has printed my point and correctly. So like before, but now with my own struct point. And I can test it further by adding other points. So I should have 2 points. And if I add the first one again, this should not be added. And that is working. All right, now that we have the program functionality correctness out of the way, what is all this stuff that was required? The first one, equal, and actually is close brother partial equal, means that we need point to have some implementation of equality, which is fairly obvious because we want our set to not have duplicates. And it seems like by default, a structure does not have equality, which is not the same as most programming languages. In other programming languages, you would have an implementation of equality for anything that you define. For Java, for example, if you define a class, it would come with the default implementation for equals, and same for C#, same for C. But the meaning of equality in these languages is may seem a bit odd for sometimes, because in these languages, if you have, in this case, if you define a class that is a point, these two values here are not going to be equal, because for Java, equality means that they are not only the same values, so here 0 is 0 and the same value 0, 0, but they must be exactly the same instance. So if I have, so if I have point 0, 0 and a point b 0, 0, if I want to see if they are equal, so if I print a equal b and then question mark, are they equal? And then do a equal b, answer. In Rust, I expect to see true, right? Yes, they're equal. But in Java, this would not be true. Java is stricter. The equality by default would only be true if I do a equal a. And actually, there's an error here. Okay. Why is the error? Equal operation as operand to equal. Oh, you see the clippy. So this is not really an error. It compiled really, but it's just saying that this is probably not what I want. But actually, it is what I want, okay, for testing. So in this case, we have equality not only because the objects are the same, but they are equal because the elements are the same. This is called structural equality, or sometimes it's called value equality. Right? And again, for Rust, this is not coming by default. Right? There's no equality at all by default. And without these two keywords, I would not have, there will be an error. Right? So if I remove this, so first remove these guys. Let's go for something much easier. Remove these boards here, comment everything here, and just focus on equality. Let's remove this for the moment, and then go back to a equal b. And you can see that I have no implementation for equals, and now the binary operation equal cannot be applied at all for point. And it says that it's because this partial equal might be missing for point, which is the case, it's missing. And it even tells me that we should consider deriving partial equal. So, which is exactly what I'm going to do, derive partial equal. So, but what is partial equal? Partial equal, if you hover it, again, there's a pretty good explanation. It's essentially saying that you can compare two elements, but you can and when you compare two elements, you have the behavior that is fairly intuitive. Yeah. For example, that when you have A equal B, then you also have B equal A. So if your equality does not have this, it doesn't. It's not equality. It doesn't qualify for equality. And the same thing here, for the second property, which says that if you have A equal B and B equals C, then A should be equal to C. So these two things here are pretty much what do you need to have a relation that can be called partial equal. And the only remaining one that's missing is the fact that every element can be compared. This is partial because you have some elements that cannot be compared. And the reason why we have this distinction is because for floats, we have spatial value, which is in the end not a number, and not a number is not equal to itself. We have this weird thing with floating numbers, where when you have a floating number that's n, it is false. It's not equal to anything, even itself. But in cases where you have also this property that every a equal a, then you can have equal. So equal is funny because equal does not add anything. It doesn't add any function. Right? So if you do partial equal, you would have this function added for you, generated for you, and the compiler will generate a function that basically tests field by field for proper equality. But if you add equal to it, it doesn't derive anything else, right? You can see that the implementation for equal is actually empty. It's because equal is what we call a marker interface. It's an interface that tells the class, tells this guy point, that we want another additional behavior, but this behavior is not implemented by a method. In this case, we're just saying that if point implements equality, it also means that it has flexibility. Flexibility means that A equal A, but this is something that is not captured by the interface. The function that we have captured by interface is EQ, equal. So I actually don't need to have equal for this operator. I'm happy to have this, and then I still can compare. I'm just going to say that it is not necessary for points to always compare to itself equal. But there are some data structures where it is important that every element is comparable. That's the case for our set, because when I insert element to a set, I want to make sure that that element is not the same as any other element. So I will have to compare the element that I'm inserting with the other elements that are already in the set. So every element has to be comparable. So in this case, if I restore the set, you can see now that it's not partial equal that the compiler needed, but it's equal. And I can implement equal just by saying that I'm deriving from it. And this derive doesn't mean that I'm using, by the way, it has nothing to do with object inheritance. It's more like code generation. So once I do that, I used to have two errors. Now one of the errors is gone. The second one, it says that the hash is not satisfied. And that's because this set implements unicity of elements by hashing the values. And hashing the values means that internally I have a container which actually quickly checks if elements are present by comparing the hash value. And hash value is a value that you need to be able to compute from the value, and the hash value has to be an integer. Right? So you can insert pretty much anything into a hash set, but provided that you give this hash function. And again, I can also use derive to provide the implementation of a hash function, which in turn we use the hashing function for each element. You would basically hash every element and combine the hashes together. Hashing is going to make my set way much faster, because if I want to compare two elements, I know that the hash values have to be the same. So first, the implementation of the hash set will compute the hash value and look that up. But a hash set is not the only way to have a set. I can also use something else called a B-tree set. And if I do a B-tree set, then suddenly it's not the same interfaces, the same traits that my values need to have. If I hover over the error, now it says all is not satisfied. So let's see if it needed hash. I don't think so. So let's try. Let's remove hash, and I can see that hash was not needed because the error is still on odd. And odd is the extension of partial equality or equality. Odd is comparison, ordinal comparison. So it's you're comparing if two values are not only equal but also like greater or lower than each other. Right. So again, we can use partial odd to begin with. Partial odd is very similar to partial equal in the sense that it has properties that you must follow. So again, this is the same. Now this is partial equal. So right, partial odd. You have transitivity. So if A is lower than B and B lower than C, then A must be lower than C. But now you have something that is quite different, which is the opposite of reflexibility, which means that if A lower than B, then B should be greater than A. So these things, these properties, are actually very intuitive. You don't really think too much about them when you use numbers, but that's because we're very used to comparing using the standard way of comparing numbers. But when it comes to data structures that are either, for example, points on an elliptical curve or geometric, when it comes to your own data structure, it's maybe not so obvious to define ordinal function. So when it comes for partial odd, same thing here. If you introduce this one, what's going to happen is that it will generate a comparison function, which will give an order to these guys. And by default, it will just compare element by element. So it's a lexical order, meaning that if two elements are lower than each other, it's either because the first element is lower, but if these two elements are equal, it's going to compare on the second one. And if this second element is equal, then it's going to go compare the third one, if there's a third one. If not, the elements are equal. So now that I have partial odd, I can see that it's still missing something, and it's still missing odd. And the same way, there's the only difference between partial odd and odd is the fact that odd is a total order, meaning every element must be comparable to another element. And now, if I have partial comparing or compare order, you can see that this code works. We saw two types of data structure that eliminates duplicate. you saw the hash set and we saw the tree set. And in doing so, we learned about derived macros. And again, derived macros are a very powerful way to have the boilerplate code automatically generated for you.